All right, everyone. Welcome to your exam day. Um, Depending on when this uh, recording may be posted on YouTube, you might have already taken your exam. If so, this will be a review for the final end of the year final. But if not, and you get a chance to review this, there's a couple of things that we haven't touched on yet. And this is also a chance for if anyone attends in person or live for them to ask questions in the future. Usually the day of the exam, I cover, it's mostly like a Q&A session, but if there's any topics I haven't covered yet, I'll get to. Um, so let's get started. Hey. All right, so we covered everything except line. We covered everything except Fisher. And there's an example in one of the practice exams. I'm not sure if it's on e-learning or another location, but so I'm going to use this as my example. It said 3s bromo dash 2R fluoro pentanoic or something acid. Okay, so first thing is the parent is pentane, so it's going to be a 5-carbon chain, and the oic acid, obviously you know it's an acid. The oic suffix, this is for carboxylic acid. Okay, so I'm not sure if you have to know those suffixes, but just wanted to let you guys know. Okay, so it looks like this. Okay, now my bromine and fluorine are going to be on carbons 2 and 3, but I don't know if they are on wedges or dashes. So you do have to guess and check because there's no absolute correct way without drawing anything. So I'm going to always put both wedges. I'm going to put fluorine here. And I always do wedges because I like to keep my hydrogens as a dash, so I don't have to flip anything. Okay. Okay. So these are going to be my main carbons. Okay. And it also tells us that carbon 2, C2, is the front carbon. Actually, instead of saying all that, I'll just draw this I. Okay, so you're looking at it from this angle. All right. So next thing is to check our chirality. So looking at C2, fluorine would be 1. This would be number 2. This would be number 3, and this would be number 4. You might be wondering why is carboxylic acid number 3 and not number 2? Because if you look at, so this carbon is bonded to, so how I like to do it is, so looking at this carbon, so that carbon is bonded to a fluorine, a carbon, carbon, and hydrogen. Okay, it's very obvious that fluorine is going to be 1 and hydrogen is going to be number 4. So we're deciding between the two carbons. So the carbons are bonded to what? So let's say this is the carboxylic acid one. So this one is bonded to a oxygen and an oxygen and a hydrogen. The other carbon is bonded to a bromine, carbon, and hydrogen, okay? So really you're looking at the first point of difference, which is bromine versus oxygen, okay? And you're comparing the two biggest atoms, in which case bromine takes priority because it's a lot bigger than oxygen, which is why the one that's attached to bromine is going to be carbon 2. So don't just assume carboxylic acid is bigger. You can't view it as a unit. And even if you combine both oxygens, it's still less than bromine.
What if even though it's a double bonded oxygen, so it's a carboxylic?
Even then, yeah.
Even then?
Yeah. Even if it's triple bond. Okay, so that is our priority for that C2. So we are gonna go counterclockwise. So counterclockwise, just to refresh everyone, clockwise is R and counterclockwise is S. And at the end of this, I'll talk about certain things you might want to, like a one-page reminder of everything that you might want to like write down. Because some people have free response, some people have only multiple choice, some people have mix. I think most people should have a mix. But if you have the chance to write like notes, I'll tell you guys what to write right when you get the exam. So this is counterclockwise, so it's going to be S, but we want R, right? So the quickest fix is to just change my chirality, or sorry, my stereochemistry of fluorine and hydrogen. Okay. So instead of wedge fluorine, I'm going to put a dash fluorine and a wedge hydrogen. Okay, because my priority is still S, but because my fourth group is on a wedge, I have to flip it. And just a reminder, if it's a dash or a wedge or a line, you keep, you flip, and you rotate. Okay, so because I put it on a wedge now, we rotate it, so now instead of S, it turns to R, which is what we want. Now let's look at bromine. So bromine is going to be 1. Carbon that's bonded to fluorine is going to be 2. Carbon that's bonded to methyl is going to be 3. And this is 4. So we are going this way, which is, again, S. And this time we want it S, and my fourth group is on a dash, so we don't do anything else. Okay? Now, there have been questions about which direction to go if my groups are arranged in this order. Okay? If my groups are, if my 1 and 2 are not right next to each other, and they're opposite from each other. So obviously, you can either go this way or this way, right? Those are your options. But you have to look at where 2 and 3 are. So you don't do 3 to 2, right? It's easier if you go 2 to 3. So that's why you go to the right, to the clockwise. And if you have a situation like this, it's perfectly fine to skip number 4 and go to 3. Okay, that is perfectly fine. And let's say you have a scenario that looks like this. I'm not going to go this way. I have to go this way. Because again, I want to go 1 to 2, but 2 to 3 is just as important. Okay, so don't get those mixed up because that will, mess up your, if you don't get chirality right, you'll get a completely different molecule. And because it's multiple choice, that could mean the, end of like the question. Anyways, so this is, we're given a nomenclature, and this is the line angle. Okay, now we're going to turn that line angle into a Newman. And again, C2 is going to be the front carbon, so we're looking from right to left. So let me redraw this. All right, so you draw your back carbon and you draw your little dot. Okay, so again, we are looking from this direction, and C2 is the one that has fluorine. It's going to be front. Okay, so looking at this, I'm going to look at where my line is. So my line is pointing downward here, and my line is pointing upward here. Okay, so because my line on my front carbon is pointing down, I'm going to draw a line straight down. So this is going to be a regular Y. If the line is pointing up on your front carbon, then it would be an upside down Y. In either scenario, it's okay to do whichever, as long as you keep everything consistent. Because remember, if you're drawing the opposite, that means it's just the enantiomer of the other. But obviously try to do the more accurate standard way. All right, so let me actually scroll down. Okay, so let me actually rewrite this a little bit bigger. Okay. Okay, don't know why it's there. Okay. I mean, okay, so right here, you have your front carbon, regular Y. So this, you have three sections. You have the left, the middle, and the right. The middle is going to be your line. The left is either going to be wedges or dashes, we don't know yet, and same thing here. So first thing first, let's do line. The front carbon is bonded to a carboxylic acid, so it can either be written like this or it can be drawn out with carboxylic acid. So just be aware to recognize both. And then my back carbon is bonded to a ethyl group, which is also known as C2H5 or CH2CH3. Either one works. I'm not sure if you can write ethyl. I would recommend not writing ethyl methyl and writing the formula. Okay, now I have to figure out which side is my wedge and which side is my dash. Okay, and let's say I don't know at all and I had to just completely guess. The fact that fluorine is a dash and bromine is a wedge should tell you that they are going to be on opposite sides of the projection, okay? So at the very least, keep it opposite to each other, okay? So the trick is, well, there's two ways, and I talked about this. You can visualize it, or you can see wherever the eye is. So whichever direction the eye is, so right now it's in the right, that's also the side the dash is going to be. So this side is going to be dash, and this side is going to be wedge. Okay? And if that didn't make sense, go back and watch last week's video. But of course, there's also the way you can visualize it, knowing that wedges are out of the page and dashes are into the page. And then so just grab a pen or whatever or a model kit and rotate it. Okay? So the front carbon has a fluorine and a hydrogen. The back carbon has a hydrogen on a dash and a bromine on a wedge. Okay? So that should be your Newman projection according to the line angle. now we're gonna go to Fisher projection, but I'm gonna go from line angle to Fisher rather than Newman to Fisher. I always like to make Newman or Newman or Fisher from my line angle, and not the other way around. Okay, I don't know why it's doing that. I'll just redraw right here. Okay, so I know this is, this is R, and this is S. Okay. All right, so I have my line, and then I have my chain substituents in the middle. So I believe different professors have different ways of explaining what goes on top. Some people say the least oxidized form. Some people say the heaviest on top. So we're gonna do COOH on top, and we're gonna do C2H5 here. Okay. Now that means these are my chiral carbons, and the fluorine is going to be closest to my carboxylic acid. Now I don't know if fluorine goes on the left or the right, but again I'm going to guess and check just like I did with my wedges and dashes. Okay. And for Fisher, unlike Newman where we said our wedges and dashes are going to be on the same side, or rather my fluorine and bromine are opposite stereochemistry, right? So that means they're opposite on my Newman. That is not necessarily true for Fisher. They're not always opposite, and they're not always on the same side. So always, take it one by one. For Fisher, you can always do chirality, while nomenclature, or while Newman is kind of harder to do chirality. So I'm just gonna put both on the same side for now, and we'll go from there. Okay, so fluorine is 1, carbon with bromine is 2, carbon with oxygen is 3, hydrogen is 4. By that logic, it is going to be S, but because my hydrogen is on a wedge, it's going to be an R. And real quick, something I forgot. These sides are all wedges, and the top and bottom are all dashes. So if your fourth group is on the side, which almost always it is, you're going to have to flip it, always. Okay? So we originally want R, we got S, and we flipped it to R, so we're good. That means the fluorine is on the left side and the hydrogen is on the right side. Okay? Just gonna check it.
So if the F was in the R, we have to switch. Since if we put F in the R, it would be an R chirality. So you still got to switch to an S.
Wait, say that again?
For that purpose.
Can you repeat that?
So if you put the fluorine on the right side and the hydrogen on the left side, the chirality would flip, right? And in that scenario, you still got to flip the chirality afterwards.
Yeah, in that scenario, you would get R, but it flips to S. So you have to put fluorine on the left side instead.
So it always flips no matter what.
Yeah.
You got to pay attention to the actual priority groups.
Yeah.
Gotcha.
Okay. All right. So we're going to do bromine again. So bromine is 1. Carbon with fluorine is 2. Ethyl is 3. Hydrogen is 4. We're going to go clockwise, which is R. And we flip because my fourth group is on a wedge to S. And that's exactly what we want. We want, wait, actually, one. Yeah, okay, I did this right. So the reason why I got confused is bromine and fluorine are on the same side now, whereas before they weren't. So like I said, don't apply the same rules to Newman as you do to Fisher, okay? Newman, for sure, they will be on opposite sides. Fisher, it can be both. They can either be on the same side or opposite sides. All right, so that's an example of this Newman this nomenclature. So I'm just gonna scroll through everything. If you guys need to take a screenshot or take note of it. So we talked about R and S, what to do if it's wedge, dash, and line, which direction to go. I talked about through like the priority and all this. Okay, and I talked about like the I and like if you can tell which side is wedge and which side is dash. And then here's the Newman projection.
For the Newman, it's supposed to be correct, but the fluorine, is to flip where the fluorine and the bromine are at.
So flip this and this.
Yeah, but keep them the same, what's it called, the same distance from each other. So the bromine will be where the other hydrogen is the same, the back carbon. The fluorine will be in the hydrogen, the front carbon.
I mean, as long as you like switch these also, I guess. Because this is bonded to this. And if you flip bromine and fluorine, then carboxylic acid would be bonded to.
If you put the fluorine in the front carbon, where the hydrogen in the front carbon is at, and then you do the exact same thing for the bromine, will that still be the exact same answer?
One sec, let me try. So fluorine where?
On the left.
Where bromine is?
No, for the front carbon. So
okay.
Right there, yeah.
And then I'm guessing that's hydrogen.
Yes.
This is still this?
The acid, yeah. And then the bromine will be on the bottom, in the bottom right.
Yeah.
So are those exact same molecules still, or is it the correct version will be the one on the left?
So the one on the right in your model, this is an enantiomer of the left.
Yes.
Which technically, I'm not sure if they'll take points off of it. I feel like technically it is right because it's an enantiomer version of it. I guess it won't be right because the R's and S are flipped, right? Yeah, I think the R's and S's are flipped in this scenario. If you're still looking at it from right to left instead of left to right. Like this, in order for this to be right, we're gonna have to look from the I has to be on this side. Yeah. Otherwise the chirality would be flipped, which is technically wrong or different. Yeah.
Thanks.
Mm-hmm. So yeah, that's the Newman projection for the line angle. And then we went back to the line angle to draw our Fisher projection. Okay. All right, so that is all of exam 1. So real quick, I'm gonna kind of talk about like the topic list. And let me pull up a picture. Okay, so actually I can just type this out. So make this bigger. So for unit 1, you have Yeah, high. Okay, you have so you have octet rule / formal charge. You have hybridization. You have sigma and pi bonds. You have functional groups, which also means IR. You have resonance, acidity / basicity. You have chair conformations. You have Newman projections, Fisher projections. Okay. You have chirality, which is the RS stuff. And yeah, I think that should be it. So as far as ranking, the type of ranking questions you can get. So you can get acidity, you can get basicity, you can get chair conformation, like cyclohexanes and the stability of that. You can get Newman projections, like anti-staggered, gauge, and eclipse, and the stability of that. You can get one of the practice exams has something called number of stereoisomers, and I can do an example of that. And then there's something else called, I'm not sure if this is talked about, but one of the practice exams also has this ranking. And I believe that should be it. If not, let me know if there's anything else. Okay. So that should be all of Unit 1. Again, because this is the day of the exam, I'm not sure how many people are going to watch the review. Or yeah, the weekly review. But for if you ever need to reference back for your semester exam, this would be a good place. All right. So real quick, I'm going to do the number of stereoisomers, just in case that comes up. So 1 equals most number of stereoisomer. Okay. Um, um, okay, so we're going to look for chiral carbons. Okay, so looking at the first one, obviously this is going to be something we're going to look at, but this is not a chiral carbon because this side and this side are both ethyls. So we actually have, before we start, there is a formula for this, so it's 2 to the n. This equals number of stereoisomers. Okay, and if it's something called meso, this is the formula. Okay, and we'll talk about, so meso just means if there's a line of symmetry and there's chiral carbons on both sides. And then N stands for chiral carbons. Okay. All right, so going structure by structure, this has 0, so 2 to the 0, any number to the power of 0 is going to be 1. The second one has 1 there, 1 there. 2 to the 2 equals 4. This one has sorry, one second. This one, only these two are chiral, and there's a line of symmetry. So this is our meso compound. So we're going to use 2 to the 2 minus 1, which is 3. Otherwise, if it's 2 to the 2, you're going to have two structures with 4, and there's not going to be a way to distinguish. So in that scenario, you should know that in ranking questions, you're always going to have something different from each of the structures. Here, we don't have that problem because there's no symmetry, so it's 2 to the 3, which is 8. And then here it's just 2 to the 1, which is 2. Okay, so obviously we're comparing 1, 4, 3, 8, 2. 1, 2, 3, 4, 5. Okay, so if you ever see a question, a ranking question like that, this is how you solve it. Make sure you know that formula. You have any questions? Okay. All right. Do you have any questions regarding any of these that you want to?
The basicity questions. The practice ones have some weird ones where they give you the conjugate basis. With the conjugate acid, my bad.
Yeah.
And it's just weird differentiating between which was the better proton, what's it called? Which one has the most, can retain the proton better, or constant protons? That is the between it.
You said basicity?
Yeah.
Okay.
It's kind of weird to conceptualize whenever you think it, which is the weakest acid.
Sure. We can talk later about that. I'm not sure if I can pull that up here. But, okay. So some things to, I guess, not necessarily memorize, but basically, you know what I mean. Okay. So things to know. Okay, and this is not in any particular order, so I'm just gonna write them as I remember. Remember that R is clockwise and S is counterclockwise. Remember that your fourth group is on a dash, you keep, it's on a wedge, you flip, it's on a line, you rotate. Remember your periodic table trend, which is being, stands for basicity, electronegativity, and acidity. Don't worry about the N until Thursday. And then there's another acronym called ARIO. This is like a checklist. It stands for atom, resonance, inductive effect, okay, and then orbital. So this is helpful for acidity ranking. Remember that resonance is the most important factor, and then atom, and then inductive effect, and then orbital. In inductive effect, you're going to think about halogens, okay? You never look at the size of halogens for, don't get inductive effect confused with atom and vice versa. And halogens, think of it as magnets. And in magnets, think about, strength of the magnet and location of the magnet, okay? Basically, where your inductive effect is located versus how effective that location, that effect is, okay? Remember how to resonate, okay? So I always use this model. Okay, and it's really important to number your atoms in this model, okay? So all that's happening is carbon 1 or atom 1 and atom 3 are flipping in terms of charge, okay? But the middle atom, atom 2, all it's doing is it's like a lever, okay? Or whatever the analogy is. It's gonna go from, to 2 to 3 to 2 to 1. So carbon 2, the middle atom will always have that double bond, okay? So if you apply this 3 atom rule to any resonance, you should be able to get all of it. Other things, obviously you know your functional groups. I'm not going to write all of them. Let's see. Chairs. Remember how to draw a chair. And I always like the lightning bolt style. So remember that these are your equilateral positions. Okay. So E, 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 E. And these are your axial positions. Okay. Okay. So a wedge means out of the page / towards you. A dash means into the page or away from you. Okay. It also means basically up and down. Okay. What it doesn't mean is it does not indicate axial or equilateral. Okay. So you can have a wedge that is both axial and equatorial. Okay. So notice how this equatorial is pointing down, so that could be a dash. And notice how this axial is pointing down, that could be a dash. Likewise, also, if I have 2 substituents that are pointing down, they are going to be cis, okay? Just like if you have 2 wedges, it's going to be cis, or 2 dashes, it's going to be cis. On the chair, look at the direction the substituent is pointing. If they're both pointing down, it's going to be cis. If they're pointing, one is up, one is pointing down, it's going to be trans. Okay? So likewise, so these are basically dashes, and this is a wedge. Okay? So I'm actually going to do that for all of these positions. So this is pointing down, so that's going to be dash, 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 wedge, 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 wedge. Okay? All right. So Newman projection, I kind of already talked about, like things to know. Fisher as well. Chirality, I already talked about right here. Isomers and functional groups, I'm not going to draw all of them. I would just go back to the other videos. Acidity and basicity we talked about. IR, again, the chart is given to you. So that doesn't mean don't study it, because you still have to know certain things. Just remember IR will also appear in OCHEM 2. Octet rule formal charge, I would hope you guys know from OCHEM, Gen Chem, and as well as hybridization, as well as sigma and pi bonds. So hopefully all of that are the easier parts. Line angle drawing, please get used to it rather than Lewis structure, because you're going to use line angle drawing for the rest of OCHEM. Okay, resonance, we've kind of talked about. Just be careful about what can resonate and what can't resonate. You can resonate with a double bond and a lone pair, and if the double bond is too far away, obviously you can't resonate. If your charge is on the double bond, obviously you can't resonate. And you want the charges on the most electronegative atom, such as oxygen, rather than carbon. And yeah, I think that pretty much does it as far as finishing up the weekly review, summarizing the exam stuff, going over this ranking problem, and then some things to know. So I'm gonna zoom out a little bit. Right, I don't think I can zoom out, but this is as far as I can go. Okay. So do you have any questions?
For the exam, whenever you're in Orgo, did they ask for like conceptual questions? Just make you actually define it?
So we can talk a little things about the exam. So when I took it, as a disclaimer, in 2017 fall, which is 4 years ago, my exam and most exams before COVID were all free response, okay, which means it was partial credit and it was out of 250 points, okay? And the entire course, if you get 1,000 points, you get 100 or like an A+, okay? And another disclaimer, if you get a 70, that's a B+ in the course. If you get 700 points, that's a B+. 70 to 77 is a B+. 77 to 80 or 800 is a A-, and then 80 to 90 is A, and 90 to 1,000 or 100 is A+. So free response means partial credit. Multiple choice does not mean partial credit. And I also believe when I took it, all the professors had the same exam. But they had different quizzes. But this year, I thought it was the same thing, but I've been hearing that some professors or the exams are not all the same, because some professors are leaving out diastomers and Fisher projections, and some are leaving out something else. So I don't think all the exams are the same, but I might be wrong. And sorry, what was your question?
There will be conceptual questions.
Yeah, so with multiple choice, with free response, obviously it's a little bit, I think it's easier because all of your practice exams in the past, PLTL, SI, pre-tutoring, it should be all free response. And OCHEM is a very free response course, okay? It isn't a good feeling to have multiple choice, depending on how you like it. So with multiple choice, obviously with resonance or any of these could be, there is potential to make it into a multiple choice question. So that means it could be easier or it could be harder. Like for chirality, you know for sure they're going to give you both options. And if there's multiple chiral centers, they'll give you all the options. As far as conceptual questions, yeah, they can ask you, you know, maybe something about inductive effects or like, I can't think of too many actually with
that's what I
this.
was wondering for, because most of it's all just show your knowledge of it when giving
Right.
an example.
I guess you'll have to wait and see because there could be, but usually there shouldn't be any conceptual questions. It's very straightforward as far as like multiple choice goes. At least from what I remember. Yeah, like I'm not sure if they'll do like ranking or if they'll do like 1, 2, 3. Sometimes they'll just say what is the most acidic or what's the most stable. So it might be that, or it might just give you all the numbers. Yeah. Anything else?
For chair confirmations, whenever they ask which has the most energy, it means which one is the worst of the chair confirmations.
You said, okay, chair confirmation, whichever
Yeah.
has the most energy.
Yes, most energy is the one that has the
Least.
worst.
Yeah, it's the least stable confirmation.
Least of harm.
Yeah. So stability and energy have an inverse relationship. So that might be confusing to some people, but just think about it like, let's say like a nuclear bomb has a lot of energy, right? Because it's, you know, it's a nuclear bomb, but it's obviously, you wouldn't call that, it's very unstable, right? Think about it like in terms of like enzymes and like metabolic pathways. If your enzyme has a lot of energy, it's likely to occur, right? And it's reactive. So if it's reactive, it's going to be unstable. So they also use the term reactivity, stability, and energy. So you can look at it like holistically, but OCHEM sometimes is just conditional. So whatever you're given, just compare those two and don't apply like outside knowledge to it. Sometimes, like especially for ranking, there might be like really bad acids, but comparatively, that is the best one. So yeah. I will say that when I took it, there were 3 unit exams and a final, and I had 5 quizzes, and 1 exam dropped and 1 quiz dropped, and obviously the final. But this year, and like previous years, they got rid of the 3rd exam, and they got rid of a 5th quiz, but they are making the final exam replacing the lowest midterm, which is similar to what they did in Gen Chem. So that, you know, depending on your point of view, could be helpful or hurtful. And I say this because this exam is very hard for a lot of people compared to the rest of the exams, because it is OCHEM is very new. It's a unique science that you haven't ever been exposed to, you know, like shapes and stuff. So it could be very challenging to just understanding how to study. But moving forward, it could be easier. Some people say exam 2 is hard because there's a lot of subjective, you know, sentiment towards like what's the right, what's wrong. some people say exam 3 is hard, or unit 3 material is hard because there's just a ton of reactions, okay? And which more or less you can memorize, but for some people that's not necessarily easy. This, in my opinion, was very challenging because not only is it unique and you have to learn how to study, but for Chair, Newman, and Fisher, it can be very challenging to visualize some of these. And even if you have a model kit, which I don't necessarily recommend because time has always been an issue for OCHEM exams, and this exam especially, I was struggling with time. But because it's multiple choice, that may cut down on time, I'm not sure. Also, another point about multiple choice is there are very clear wrong answers. So keep that in mind and try to eliminate wrong answers instead of always trying to figure out the right answers. Okay? And also, just maybe throughout, like, studying for this exam or like the past 4 or 5 weeks, there's lecture, there's your professor, TA, SI, PLTL, peer tutoring, weekly review, all that, different tutors. There might be conflicting information. Obviously, go with whatever works. And even some exams, practice quizzes, there could be potential key errors. So always make sure there's no like error. And if there is an error, like obviously that means you were right and not the key or whatever. So whatever works for you, stick with that, because you're gonna hear like different ways on how to do, chair confirmations. Oh, one thing I forgot to mention is I have this template. I feel like SI and maybe some other tutor might do this also. And I don't know if they do this in class, but you can use like a template going from cyclohexanes to chairs to understand if it's equilateral or axial or equilateral, or sorry, equatorial. So if they're all wedges, this is just a template. My position is going to be alternate. Okay, so let's say I have so based on this, I know these are going to be equilateral or equatorial. Okay, and if I have something like this, if I have a dash, all I have to do is flip that position. So if it's normally a E, it's going to be an A. If it's normally a A, it's going to be E. So whatever works for you. So the more E is equals more stable. Okay. So there's something called a 1,3 diaxial steric hindrance, and that's when your groups are in axial positions. Those positions are going to interact and bump into each other. So that's what steric hindrance means, is you have electron clouds from your substituents, from your carbon, hydrogens, and all they're going to, when they clash together, it becomes unstable. It's gonna, it's gonna be likely to react, which produces energy. Okay, which is why you always want your bulkiest group in equilateral positions, so it's not interacting with axial like steric hindrance. All right. Okay, so I think that should be most of it. Obviously, I would recommend doing lots of practice problems. And definitely studying, week by week instead of, starting from Monday. All right. So I'm gonna scroll back to this in case anyone needs to look at it. I'm gonna scroll. Okay, I don't see any questions in the chat here. Okay. All right, so that will be the end of week 5 weekly review for Unit 1. Next week we'll talk about Chapter 4, which is going to be about carboanions, carbocations, and like chlorination, bromination, all that. So we'll continue on with next week. I hope everyone does well on their exam.